So I will give a quite brief introduction to nucleosynthesis and chemical evolution of the universe. As Muriel said, I'm from Geneva, and usually it's not me that is here to give this lecture. It's Sylvia Ekström, one of my colleagues in the group. Unfortunately, she had elbow surgery a few days ago, so she was not able to come here, and I'm here to replace her. So I would like to thank her for providing me with the slides of this course, because I have quite short notice and I would not be able to do all the work here. So thanks to her for that, and I will try to replace her as much as I can. So chemical evolution of the universe is a quite big topic, so I will basically cover 14 billion years of evolution from the very beginning up to now, and try to see how from the starting point, from the Big Bang, universe proceed to build the chemical elements we are built of, basically all what is not hydrogen and helium. So we will start from this view here. That is a picture of the cosmic microwave background. That is basically the first light of the universe that was emitted roughly 400,000 years after what is called the Big Bang, to something like that, which is somewhere in the Amazonian forest in Brazil. So I will start, this is basically what we have in the solar system. So it's the relative abundance of various kinds of elements. What we have in the sun, so you can see here the relative abundance of these elements, and here the elements sorted by their nuclear mass number. So you can see that depending on what element you're looking at, the relative abundance are very different. So basically you have a lot of hydrogen, a lot of helium, you have very few lithium, beryllium, boron, and then you have various elements with carbon, oxygen, neon, silicon, and so on, that goes up and down here. Here you have basically nothing, then you have a strong peak at the iron, and so on. So I will try to explain you a bit how this diagram was built during the history of the universe. So the outline of the lecture is the following. So I will start with a quite long introduction that will basically present all what I will say later on, but as a kind of general introduction for people that are not in the field of astronomy. This can be useful to fix a bit the idea before going in a bit more detail. And then I will go through three main parts, which is the primordial nucleosynthesis. So basically the nucleosynthesis that happened during the Big Bang. Then to stellar nucleosynthesis, so how stars are making other chemical elements, and then how this is mixed to make the universe evolve in terms of chemical composition. So the principal actors of our movie are the forces that are found in our universe. There are mostly 4 of them. The main important for astronomers is gravity. That is a bit special because it is not in the same formalism as the other one on a theoretical point of view. But the other ones are important as well, particularly for building the chemical elements. So there is an electromagnetic force that we are quite used to in everybody's life, which is the electrics and magnetic interactions, so electricity and so on. Light is in this category as well. And there are also 2 other forces in the universe, the weak force and the strong force. Weak force is responsible for radioactivity, beta disintegration, and so on, and interacts with a weak current through a kind of particles that are called Z and W boson. The neutrinos are part of this force as well, and the strong force is responsible for the cohesion of the atomic nuclei and the quark, how quarks interact between them and build protons and neutrons and things like that. It's sometimes called color force because the charge of this force is a color and interacts with particles that are called gluons. And yeah, the particle for the interaction of the electromagnetic force are the photons that are our light particles. So basically, we will try to understand how this diagram is progressively built through the evolution of the universe. So this is a well-known Mendeleev table where the elements are sorted starting from the lighter one to the more heaviest one here. And the columns are made according to given properties of the element. So we will see how this diagram is progressively built during the time of the universe history, and where these different elements are built, because they do not come all from the same location or the same time during the evolution of the universe. Another diagram that will be quite useful for us is this kind of plot here, where you put the elements according of their proton numbers and their neutron numbers. This is quite important because the proton number, which is usually marked as a Z, defines the element you have. Basically, it defines the number of protons in your elements, and because usually the elements are neutral, it also fixes the number of electrons of your elements. So as elements interact, atoms interact between each other through their electrons, most of the time, these proton numbers and these electron numbers determines the type of element you have. So this is usually along this axis here, and on the other axis you have the atomic number, which is the number of protons plus the number of neutrons in a given nuclei. So this defines the isotope. So you can have for a given element different isotopes that are more or less stable and can disintegrate or not. So starting here, you have at 1, the hydrogen, which is only 1 protons. And then you have, for example, for hydrogen, 3 different isotopes that are the hydrogen 1, the hydrogen 2, which is usually called deuterium, and the hydrogen 3, which is the tritium, for example. And the same for all of the elements, and you can see that depending on which one you're looking at, you can have a very big number of different isotopes for a given element. What is shown here is the elements that are the most stable. So in black, you have basically the stable elements, and you can see that they are not spread everywhere in this diagram, but they all lie in this kind of diagonal where the number of protons is roughly equal to the number of neutrons. So the stable elements tend to have roughly the same number of protons and neutrons in their nuclei. Going to higher proton number, you can see that you need a bit more neutrons to stabilize the nuclei. But basically, this is where you have stable elements in this diagram, and the yellow zone are the elements that are not stable, and you can find sometime during some nuclear process, but they will disintegrate to this stability valley here in the middle of this plot. So finally, here is the background scene of our history, which is what happens to the universe during all this time, during roughly 14 billion years. So we know that in very long time ago in the past, the universe was much hotter and much denser than now. And this is basically what we call the Big Bang model. And we learned that from the legacy of the general relativity of Einstein that allow us to draw a big picture of the evolution of the universe. So then if you add a bit of nuclear physics during the first few thousand years of this history, you will learn what happens during this very first time of the evolution, where the universe was very hot, and what happens to all the particles during this time. Then you have suddenly the emission of the cosmic microwave background. I showed you previously. We'll see what happened at this time. And then you have the evolution of the universe during the time where you have first what we call the dark age, where the universe was mostly neutral without stars. Then the stars formed, re-ionized the whole universe, and then the light can travel freely in the universe. The building of the first galaxies, and then the formation of the Milky Way somewhere here, formation of the solar system roughly 4.5 billion years ago, and then we are somewhere here. So this is another view of this timeline, zoomed, focused on the very first time between, let's say, 0 and 380,000 years, where the CMB was emitted. So at the very beginning, we have something that is called the Planck time, which is a kind of limit of our knowledge, where we know that general relativity and quantum physics should work together to learn us about what happened there. Unluckily, we have so far no theory, or only a kind of sketch of theory that are mixing these two different big fields, that are the general relativity on one side and the quantum physics on the other side. So we don't really know what happened at this very first time here. But starting from here, we have a good knowledge of what happened between, let's say, 10 to the minus 10 seconds after the Big Bang to roughly this emission of the CMB, thanks to particle accelerators and this kind of instrument that allow us to study the physics at these high energies and tell us what can happen during this first stage. So you have different events that are important for the nucleosynthesis, the primordial nucleosynthesis. So you have first the electroweak symmetry breaking, where the electromagnetic force and the weak force decoupled from each other. Then you have the formation of protons and neutrons, roughly 10 to the minus 4 seconds later at still quite hot temperature, 10 to the 12 Kelvin. Then you have the neutrino decoupling after 0.1 seconds at still lower temperature. And then as the temperature decreases, you go to a lowest and lowest energy reaction. So you authorize the formation of different type of elements. So you have first the deuterium synthesis at 1 billion degree roughly after 1 minute. And during this 1 minute and this 16 minutes, basically all the nucleosynthesis that is allowed during this history is made. So after the first 16 minutes of the evolution of the universe, you have finished with the primordial nucleosynthesis. Sorry. Then you can have kind of gas phase chemistry here to build some first molecules. And then after this 400,000 years time, the universe is not hot enough to keep the hydrogen and all the other elements ionized. And from this, the light can travel freely through the universe. And thus, from this point, we are able to see something from this time. So the CMB was emitted at that time at very hot temperature. And from then, due to the expansion of the universe, these photons were progressively shifted at lower temperature, but we are still able to detect them today at approximately 3 Kelvin, so 1,000 times less energetic than at the point where they were emitted. But they are very useful for us to learn what was the state of the universe at these very first stages. What is important here for the process is not really the time, but the temperature. So the temperature fixes the different processes that can occur. Temperature is a measure of the energy in this very first stage. To build up the time, the corresponding time, we have to rely on a model of the universe. So there are a lot of assumptions that are hidden behind this time. You need to know the different type of content of the universe, how many radiation you have, how many baryonic matter you have, how many dark energy you have and dark matter you have, and things like that. So this is dependent on what model you assume for the universe. But it is computed from how the universe heated or was more denser in the past. So the real scale, if you want, is the temperature one. The time scale rely on different kind of assumption and models to be converted from temperature to time. So what we call the lambda CDM, so lambda cold dark matter model, is the how to say, the more reliable model we have so far, by different means of measuring what happens to the universe during this very first time. And we have nothing better so far, but there are a lot of hints that indicate that this model is not that bad. So far it's the best we have. So the primordial nucleosynthesis basically build up hydrogen, helium, lithium, and beryllium. It was so fast, and the temperature decreases so fast during these first 16 minutes that nothing else can be made at this time. So after the Big Bang, after this first 400,000 years, the universe was composed essentially of 75% of hydrogen in mass, 25% of helium, and traces of lithium and beryllium, and other isotopes of hydrogen and helium. So the periodic table is still scarce, mostly empty at this point. And if we had to stop the stories there, the universe would have been a bit boring, and probably nobody would care about exobiology so far, because probably we would not be here to discuss. So what happened then? So the universe gets transparent at this CMB emission, roughly 400,000 years after the time zero, if you want. What is shown here is a map of the temperature of the CMB. This is a map of the full sky. So you have to imagine that this kind of ellipse is surrounding you everywhere. And the color map indicates the temperature. So you see that there are variation all around the sky for this CMB temperature, but they are really, really small. So the difference, the relative difference between the blue and the green and the red is only 10 to the minus 4. So the universe was really, really homogeneous at that time, but not completely homogeneous. So these tiny fluctuations that are found here at this, this is another measure of the time, so it's called the redshift. So this is the time of the CMB. So you have this kind of fluctuation that are coded here as a temperature, but you can also tell that this temperature fluctuation are density fluctuation. So here you have some density perturbation if you're in your universe. And then as time proceeds, this density fluctuation will grow. This is due to the gravity. Gravity and time makes that the small overdensity you can have at some point in the universe will progressively accrete matter from the surrounding, and thus you will make the overdensity more dense and the underdensity less dense, and you will accrete matter progressively with time, and you will form after sometimes bound objects that will be the galaxy later. So you have here a cube of universe, and the blue represents the gas density. So starting from a very, very homogeneous universe, you progressively, as time proceeds, forms some kind of filaments and some kind of more dense region that progressively accretes more and more matter and will form the first protogalaxies. So this takes quite a long time, but gravitation is patient, and thus you will form at the end the first dense structure in the universe. So you will get the gas at the same place, and you will build some big voids in the universe. But at the end, you have something that looks like the universe we have today, with galaxies spread along some filaments with some more dense region at some point where we have galaxy cluster or galaxy supercluster. In these galaxies where you collect a lot of gas, gravity will continue to work and will progressively form the first stars in the universe. So stars are born in this kind of nebulae here that are called cold nebulae, where you have a huge amount of gas that will, for some reason, become unstable and will collapse and forms a lot of stars, young stars here in blue, for example, that will light up after a few million years after the Big Bang. So, what is a star? Stars are big hot gas balls. Two forces are important for a star. The first one is gravity, that tends to bring all the matter towards the center. And as you know, when you compress gas, you will increase its pressure. And at some point, the pressure can counteract the effect of gravity, making something stable over time and allowing a star to live for some time. To produce the needed pressure to sustain the gravity, the self-gravity of the star, you will produce quite a hot temperature at the center of the star. So you probably know that when you compress a gas, you tend to heat it a lot. So at the center of star, you will reach very high temperature that will allow to build the first chemical elements. So starting from hydrogen, a big ball of hydrogen, and with a part of helium that comes from the Big Bang nucleosynthesis, stars will progressively be able to burn their helium and convert it in hydrogen and convert it into helium in the center. And then successively, the stars will continue to contract when there are no more fuel available to produce the temperature needed to counteract gravity. The star will contract, heat up a bit, and reach temperature where it is able to build the successive elements. So after hydrogen, you will be able to burn helium into carbon and oxygen, and so on. And at the end, you will have stars with different kind of layers. So near the surface, you will have the initial composition with a lot of hydrogen and helium. Then you will have successive layer where you will find helium, oxygen, carbon, and then depending on the kind of star you have, the initial mass of your star, you will have neon, you will have silicon, sulfur, iron, and nickel at the very center. So this is one way to build some elements after the lithium and beryllium that were built during the primordial nucleosynthesis. So with this kind of nucleosynthesis, you can go up to the nickel 28. So it's still not complete, but it's a first step towards what we have today. At the end of their life, the low-mass stars will expel their external layers and will enrich the universe with the material they have in their outer layer. For low-mass stars, it's not very different from what we have at the end of the primordial nucleosynthesis. So this is not a very efficient way of enriching the universe. But in the outer layer of this low-mass star, sometimes you have some exotic process which are called the S processes that are able to produce some other elements and progressively fill this periodic table of the elements. So you have all this kind of element here that can be built in this way. Finally, the more massive star explode at the end of their life as a supernova. And during this phase, you will have a strong nucleosynthesis as well in another fashion that is called the R process. We will speak of these two processes a bit later on. But supernova will completely spread out the stellar material in the universe and will enrich them with some other kind of elements that are the red one here. So basically, we have filled this table through these different steps. So primordial nucleosynthesis that builds only the lighter elements. Then the nucleosynthesis that occur during the first part of the life of stars, between here, the Bohr, up to the nickel. And then for the heavier element, you have two different ways of producing them through S or R process that take place at different location in the star or in different kind of stars. But this is how you progressively build this periodic table. So I'm done with my general introduction. I will now go in a bit more detail through these different kind of processes and start with the primordial nucleosynthesis again. So yes, if you have any questions, don't hesitate to interrupt me when you need. So let's go back to the first steps of the evolution of the universe. So you have this different successive event that occurred during the first 400,000 years here, which covers the very beginning of the universe. So again, time here is more or less indicative and is built on a model. The relevant scale is the temperature scale here. So we start at the very beginning with a Planck time that is very soon after theory crashes and very high temperature, 10 to the 32 Kelvin. After the Planck time, you have an episode that is called the inflation that was needed to explain why the universe is so homogeneous. That was the first surprise when the people had a look to this CMB that I showed previously, that the universe is extremely homogeneous at the time of the CMB emission, and this was a kind of surprise because it was not easy to explain why the universe can be so homogeneous at everywhere around us. So to explain this, cosmologists had an event that is called inflation at the very beginning of the universe history, and it's just a brief period of time during which the universe grows exponentially. So this very, very fast expansion of the universe has completely removed the heterogeneity that could be present before it, making the universe extremely homogeneous. After that, you have, as you go toward us in time or at lower temperature, different kind of things that happen to the particles. So first, there is the confinement of quarks into nucleons. So basically, at this time or this temperature, the quarks that were free to go everywhere before that due to the very high temperature cannot stay isolated, and their only way of surviving was to be confined into the nucleons. So basically, the protons and neutrons were built at that time. Then a bit later, you have the decoupling of the neutrino, the mu neutrinos and the tau neutrinos. So maybe you know, I don't know if you know, but maybe yes. Neutrinos are very light particles that are that intervenes principally in the nuclear radioactivity, the beta disintegration. And there is 3 families of neutrinos that are called the electronic neutrinos, the mu neutrinos, and the tau neutrinos. The neutrinos we are used to are the electronic ones because they are able to interact with the electrons. The 2 other ones are linked with 2 other kind of particles that are called the mu and the tau. That's why they are called like that. But after this time here, roughly 0.1 second after the Big Bang at this temperature, these 2 family of neutrinos were not able to interact with anything anymore. So since then, they were free to live their life without interaction with anything else. The electronic neutrinos were able to interact with electrons and protons for a few more times, for an additional 0.9 seconds up to a slightly lower temperature. This is because the stable particles, the stable nucleons, are the protons, and the lightest other leptons are the electrons. So basically, there were nothing to interact with these 2 families and neutrinos, but still the electrons and proton remains, and electronic neutrinos were able to continue to interact with different kind of this kind of particles after this. Then after a while, temperature decreased to 310 to the 9 after about 10 seconds. And at this time, this interaction here made that there was a lot of photons that were emitted at that time. So basically, when you have a temperature higher than this one, the photons are energetic enough to interact with themselves and produce pairs of electrons and positrons. When temperature goes below this 310 to the 9, the photons were no more energetic enough to produce this kind of reaction. So basically, all the electrons and positrons annihilate themselves up to there was no more positrons in the universe, and this produced a huge amount of photons that still remain today. After this, you have the Big Bang nucleosynthesis that started at roughly 100 seconds and goes for the first 15 minutes of the universe. The typical temperature are from 1 gigakelvin up to 10 to the 8 Kelvin. So we'll come back to this a bit later. Then you have the recombination there, where the electrons were no more able to be free and were bind to the hydrogen and helium nuclei that were produced during the nucleosynthesis. So from this, the universe is transparent and the photons are free to go. And this is the emission of the CMB we have seen before. Then, after a few couple of hundred of million years, you have the first star formation that were able to reionize the universe. Today, the universe is mostly ionized due to stars. And at the very end, we have today, after 13.7 gigayears, and the temperature of the CMB is now roughly 3 Kelvin. So at the time of the emission, it was 3000. Now it is 3 Kelvin, and it will continue to decrease over time. So what happened during the first 3 minutes? So this is the interaction that take place at around 100 gigakelvin, so at roughly 10 milliseconds. So the weak interactions are at equilibrium at this point. So the electrons and the neutrinos are at equilibrium through this reaction. You have pairs of electrons and positrons that can produce neutrino and antineutrinos, and the reaction goes the two ways. The neutrons and the protons are at equilibrium as well through this reaction here. So you have protons plus electrons that can produce neutrons plus electronic neutrino and so on, or this one here, a neutron plus a positron that makes a proton plus an electronic antineutrino. But as time goes, temperature decreases, and at roughly 100 milliseconds, you drop to this 20 billion Kelvin temperature. And at that moment, the expansion rate does not allow this reaction to take place anymore. So basically, the neutrinos, the mu neutrinos and the tau neutrinos freeze out, because this kind of reaction were no more possible for them. But as I told previously, the electronic neutrinos can still interact with the baryons that are present there, so with the protons and the neutrons. That is not possible for the other flavor of neutrino. So after 1 second, temperature drops to 10 billion kelvins, and then the neutrinos, the electronic neutrinos, get decoupled from the baryons. So this event is called the neutrons freeze out, and at that time it fixes the protons to neutron ratio in the universe. So basically this ratio is determined by the difference of mass between the protons of the neutrons. It is quite small, but still there is a mass difference between the neutrons and the protons, and the temperature at the time of this event occurs. So this fixes this ratio at 1/6 with this difference of mass between the protons and the neutrons. So this means that today in the universe there are 6 times more protons than neutrons. Then the neutrons' density are governed by the beta disintegration. So the neutrons are not stable particles. They have a lifetime, a half-life of about 13 minutes. So they will start to disintegrate progressively. So you have an exponential decay of the number of neutrons since this moment, this fraction here. And it will decrease slightly over time, up to the temperature is low enough to allow the formation of deuterium. So before that, you cannot build deuterium, or at a very, very small amount, because the photons are so energetic still that you are able to instantaneously photodisintegrate your deuterium. So your protons and neutrons will produce a deuterium nuclei that will be instantaneously break up by the photons and so on. So you have a kind of equilibrium before that, but at some moment the temperature will go down sufficiently and the photons are not energetic enough anymore to break the deuterium. So since that time, the neutrons can be trapped in this deuterium, and this will save them from the disintegration of their when they are single. So this is called the deuterium bottleneck because as long as your temperature is too high, you are not able to go below the deuterium because it is instantaneously destroyed. But at some moment, that is at 10 seconds, this temperature goes down sufficiently, and at this temperature, the photons are no more energetic enough to produce this reaction. Photons plus photons make electrons plus positrons plus electrons. So since that, you produce a huge number of photons in your primitive universe. And at 1 gigakelvin, the deuterium is no more breaked, as I mentioned previously. So you can, from that, build things on top of your deuterium. So as you will have this deuterium reservoir, you will be able to produce other elements through these 2 channels. For example, you can produce tritium by accreting an additional neutrons on your deuterium, or you can produce helium-3 by making interacting 2 deuterium and emitting a protons, and helium-3 is produced through this channel here. So, or you add protons to an atom, nuclei of deuterium, or you make 2 deuterium interact and emit neutrons to produce your helium-3. So the ratio of these different elements is set up by the temperature. So this is illustrated here in this plot where you have the mass fraction of the different element as a function of temperature here, expressed in billion Kelvin, or time here, where you have 1 minute here, 1 second here, and then 5 minutes, 15 minutes, and 1 hour, and so on. So at the very beginning, at high temperature, you basically only have protons here, this cycline, and neutrons. Very few deuterium, because it is produced and destroyed immediately, and still less hydrogen-3 and helium-3. When the temperature starts to decrease, these elements are not destroyed anymore, so you have an increase of the mass fraction of deuterium here, for example. And then at some point, even the deuterium will remain stable long enough to start to build this kind of element here. So the fraction of deuterium will decrease again, and you will have a strong increase in the helium-4 fraction, the helium-3 and hydrogen-3 fraction here, due to the fact that you are able to go through this reaction because deuterium is stable enough at this temperature. Then you have the production of helium-4 built on top of this tritium and helium-3. Basically, from these elements, you have some troubles to go to higher elements because there are no stable elements with atomic mass 5 and 6. So basically, you have to jump to 7, and this is quite difficult. You can go to lithium and beryllium through this two reactions here, but you need to make your tritium and helium-3 interacts with an alpha particle. And as the universe cools down and expands, the density drops as well. These reactions are very difficult to obtain during the Big Bang nucleosynthesis. So basically, you will only produce some traces of these two elements. So at the end, now where after the primordial nucleosynthesis, you have the composition of the universe after this event. So mostly protons, neutrons, and traces of other things, mostly helium-3, hydrogen-3, and a bit of lithium, beryllium, or lithium-6. So this is the numbers that are predicted from this Big Bang nucleosynthesis. So once you know how the reaction proceeds, at which temperature and which density, you can make some models of your Big Bang nucleosynthesis and predict what ratio you expect after this nucleosynthesis took place. So basically, you have these numbers for the ratio of deuterium to hydrogen, helium-3 to hydrogen, lithium-7 to hydrogen, and this mass fraction of helium. So usually in astronomy, we mark the helium as a Y. So at the end, you expect roughly 25% in mass of helium, and the rest is mostly hydrogen, because these fractions are very small, so you expect 2 10 to the minus 5 in mass fraction of deuterium, 1 10 to the minus 5 of helium-3, and very, very few lithium-7, which is something like 5 10 to the minus 10. This is depending on this number here, that is explained here. It's the mass, the density fraction of baryons in the universe. When you count what you have in the universe, you have this fraction of baryons that is the free parameters of the models, and it is usually fixed to roughly 2%. So the energetic content of the universe is only 2% of usual matter. So you can play with this parameter, making it vary. You will change this number here, and basically you can also put the observation on top of that, so you have this kind of value that are observed. So basically, with this value of the omega b parameter, you have very good agreement between the observation and the predicted nucleosynthesis. This number is fixed by other means. It's not just because this number works the best. You have other way of determining this this fraction of baryons in the universe, and thus it's kind of a way to check that the standard model for cosmology, so the lambda CDM model, is robust. So this is one of the pillars of the Big Bang. So you can see that these three numbers here works pretty well. It's a bit worse for the lithium, which is predicted at 4, 5, and observed at 1. But lithium is very difficult to observe young enough to be at the primordial abundance. Lithium is destroyed by stars. So as soon as you have star, you destroy lithium. So you expect that the abundance of lithium in the universe will decrease as a function of time. And this is why this number here is a bit less than the one we expect. So it is not a major problem so far. So basically, that is what we have at the end of the primordial nucleosynthesis. So why there is no stable element for A equal 5 or 8, as I mentioned before. So basically, you have these isotopes for A equal 5. You have helium-5 and lithium-5, and you see that they have half-life that are extremely short, of the order of 10 to the minus 22 for these two here. And with A equal 8, you have lithium, beryllium, bore, or even carbon-8. But again, the half-life are very short. So particularly for beryllium-8 and carbon-8, you have something that is 10 to the minus 17 or 10 to the minus 21. For lithium-8 and bore-8, it's of the order of 1 second. But it means that these elements are almost destroyed as soon as they are built. And the universe has cooled down a lot and is less dense than when the nucleosynthesis took place previously. So the temperature is below 300 Kelvin typically. And this is why primordial nucleosynthesis stops before any elements with A bigger than 12 might be produced. So this is, what kind of time is it? Okay. This is the starting point of, we have a kind of adage here. So starting from nothing and having only 15 minutes ahead, one cannot achieve great things, and the saga will resume in the stars. So this is what I wanted to say for the primordial nucleosynthesis. Let's go to stars. So life of stars in one plot. This is also the grid cycle of the matter in the universe. So basically, everything starts in this kind of cloud of dust, molecules, atoms, with different kind of elements in it. But at the very beginning of the universe, it was mostly hydrogen, helium, and the traces of lithium and beryllium and bore we told previously. So for some reason, this kind of cloud are not stable and can start to collapse. So this will produce a given number of stars from this cloud. You will have stellar formation, and progressively, by contracting the matter, you will produce stars. So sometimes star can have planets, planetary system with a different number of planets, and even life, at least in one example. Stars are not there forever. They are living for a while. It depends on their mass. We'll see that later on. But basically, stars evolve, and at the end, they can become different kind of evolved stars that can be red giant, red supergiant, or Wolf-Rayet stars. And depending on their mass there, their fate will be slightly different. They can have some stellar winds that can be strong for different kind of stars that will refurnish the interstellar matter with with the gas that was trapped in the star. At the end, low mass stars become planetary nebulae, and again they expel a lot of gas and dust that go back to the interstellar cloud. But there is a small remnant at the end that is called a white dwarf that goes to the cemetery of stars. That is matter that is trapped in an object that is here, for example, a white dwarf, and that cannot be used anymore to enrich the universe. The more massive stars can go through this channel here with a supernova explosion that will bring back matter to the interstellar cloud again, and the remnant of that rest after the supernova explosion is or neutron stars or black hole that again goes to the cemetery because this matter is lost for the universe. But a lot of matter from the external layer of the star will go back to this interstellar clouds. So basically, the elements that are progressively built in stars during its life here have different ways of going back to the interstellar medium, where it will be used to form new stars that are slightly enriched in different kind of matter that was produced by earlier generation of stars. So basically, matter cycle here. There is a bit of loss in the remnant, but it's not big. It's not a huge number that is trapped here, and that's how you can go from stars with the composition of the primordial universe, so hydrogen and helium, to stars that have different kind of chemical composition. For example, the sun that has a quite different composition than the primordial one. For example, the sun has a content of heavy elements of about 1.4%, and it was almost zero at the time of just after the Big Bang. So maybe one thing you have to know and to take care here is in the astrophysics field, we called metal everything that is not hydrogen and helium. So for people that comes from other field, it can be a bit strange to know that I don't know, carbon is a metal or xenon is a metal or things like that. But for us, everything that is not hydrogen and helium is called generally a metal. And that's why generally this big cycle here will contribute to increasing the metallicity of the universe. So the metallicity of the universe is by definition zero just after the Big Bang, and increases with time, and the sun has a metallicity of 1.4%, and some other stars have a higher metallicity that can go up to 2 or even more %. So in 14 billion years, the stars were able to change the general chemical composition of the universe, making 1 or 2% of metals since then. So it's not a lot, but still it allows us to be here. So how do we model a star? So we have different kind of things we have to solve to produce a good model of stars. So sorry, I have only a few equations, but still it's important maybe to know how we do to predict things about stars. So basically we have a very generic equation, that is the mass conservation equation, that linked how the mass is distributed as a function of the radius with the content of the star, so the density inside the star. Then we have an important assumption here, is that the stars are stable. So they are in equilibrium between the gravity force here that tends to collapse the star and the pressure gradient here that tends to make the stars that counteract the effect of this gravity. So basically, a star is at the equilibrium between these two forces, the gravity and the pressure gradient. Then you have things relating the energy production and energy transport inside the star. So you have the luminosity. So what we call luminosity in the stellar community is the power of your star. So basically, the unity of the luminosity is the watt. So how this luminosity varies inside the star as a function of what are the sources of energy inside your star. So you have here, you have here epsilon, which is the nuclear energy generation rate inside your star. So one thing that will change the luminosity is how elements are burnt inside the star. And the other terms here is due to the gravity. So contraction or expansion of your star will also change the energetic budget of your stars. If you are expanding your star, you will need energy to expand your star. If your star is contracting, the contraction will provide energy to your star. And finally, you have this equation here that tell us how the temperature is varying inside the star. So it's linked to the luminosity as well, and different things, including here this kappa, that is the opacity of your matter. So depending on how your matter is transparent or not, the energy can travel more or less easily inside your star. So this is what we call the structure equations. And this is what we need to solve to make a stellar model. So if you count what you have here, you will find, I think, 7 different variables that are the mass, the radius, the density, the pressure, the luminosity, the epsilon, the temperature, and that's it, the kappa. It's 8 different equations. One is the one we are integrated in, so we do not count them. So it makes 7 different variables, and we have only 4 equations. So to complete the system, we need different other kind of equation that linked density, pressure, and temperature. This is basically what we call an equation of state. So most of you know at least the perfect gas equation of state, probably. We will see that this is a reasonable assumption for stars, but we have different kind of equation of state for different phase when the star is more or less degenerate, and so on. And we have something that we are not able to compute by ourselves. It is basically the opacity, kappa, and the nuclear reactions, epsilon. So that comes from some tables of people working in atomic physics that are able to tell us, okay, if you have this mixture of elements at this temperature and this density, the opacity will be like that, and the same for the nuclear reactions. We have tables of different kind of reactions telling us, okay, at this temperature and density, you will have this kind of reaction, and they will produce this amount of energy inside the star. So once you have all this, you are able to solve these equations here and make a stellar model. So what are the characteristics of stars? So to start, we can observe stars. So you take a telescope and you have a look to the sky around you, and you will find that in this kind of plot, the stars are not randomly spread around, but they are lying on different kind of sequence. So this work was first done by 2 different people, Hertzsprung and Russell. So these kind of plots are called the Hertzsprung-Russell diagram, and they relate here the surface temperature of the star in the x-axis where the hottest stars are here on the left and the coolest stars are here on the right. So typically the temperature here that is indicated here, I don't know if you are able to read, but it's around 2500 degrees here, and the hottest star here have surface temperature at, I don't know, 50,000 degrees. And on the y-axis you put the luminosity of your star. So it's in a logarithmic scale, and the luminosity of the sun is put to 1. So the sun luminosity is here, and you can go to 1,000,000 times the sun luminosity, or on the other way to very low 10 to the minus 6 or 7 times the luminosity of the sun here. So if you take some stars around us and you put them in this kind of diagram, you see that most of them will fall in this sequence here. That is called the main sequence. So most of the stars will fall in this sequence, and you will find very few of them here. You have here the giant branch, where you have again a kind of bulk of stars, and some other will lie here over, and very few here that are mostly the white dwarfs that are here below the main sequence. So the sun is somewhere at 1 solar luminosity and at roughly 4,000, 5,000 degrees here. So between 5,000 and 6,000 degrees here. So the sun is this star here. You have different kind of stars. So the typical masses are indicated here as well. So you see that low mass stars tends to be cooler and less luminous than the sun. Hot stars tend to be more luminous than the sun and with slightly higher masses. And you have also different. These green lines in this plot are iso-radius. So all the points in these lines have the same radius. So 1 solar radius is here. The sun is obviously on this line. And you see that stars that are in these regions tend to be very big. You can have stars that have 1,000 times the radius of the sun. On the other hand, when you go in this region here, you have very small stars with radius that can be 1/10 or 100th or 1,000th times the solar radius. So basically, this diagram tells us where the stars are, but it is not telling us how stars evolve in this kind of diagram. So it's the same as when you're walking in the wood and you see the tree around you. You can try to sort them by different means. Here one mean is temperature, luminosity. Maybe you will find a way to put your trees in a graphic where you will find some kind of structure. But just looking at trees, you need a step more to understand that the small trees are probably young ones, and then they will grow and get bigger. Or you have maybe different kind of trees that have different size and things like that. So you will need something more to understand how stars will evolve in this kind of diagram. This is only one snapshot of what you see around you, but you need more, and that's why we need the stellar modeling to understand what will happen to stars in this diagram. Here is the same kind of diagrams. So again, the effective temperature of the star, so the temperature of the surface of the star as a function of the luminosity for different kind of initial mass. So you have here very low mass stars, 0.8 times the mass of the sun, very massive star, 120 times the mass of the sun, and this is not exactly the same plot as here, because here you have only points where the star lies. In this plot here, you have the results of the models, so you will see here how stars are evolving in this diagram. So one important thing that you can learn from stellar evolution is the mass-luminosity relation. So basically, the luminosity of a star is determined by its mass at the power of 3. So you can see that this here because you have this, for example, the 1 solar mass tracks here that has basically the 1 solar luminosity. And if you go to stars that have 100 times the mass of the sun, so 10 to the 2, their luminosity are 1 million times the luminosity of the sun. So you have this ratio here. So if you have a mass that is 100 times the mass of the sun, you will have a luminosity that is 1 million times bigger. So basically, what is fixing the luminosity of your star is the gravitational contraction. So if you have a 1 solar mass star or a 10 solar mass star, its luminosity will only depend on its mass and not at all on what is the way for the star to produce energy. So you can replace the nuclear energy by whatever energy you want. You will always get the same luminosity for a star. So this is an important point. But the duration at which the star is able to sustain this luminosity is determined by what kind of energy is produced in the core. So basically, the lifetime of a star is determined by the energy available inside the core of the star divided by its power, by its luminosity. So the energy content of the star is given at most by the relation of the well-known Einstein relation. So it is the mass of the star times c square. And the luminosity, as shown here, is proportional to the third power of the mass. So what we can learn here from this very raw estimate is that the lifetime of a star will go as the mass to the power of -2. So if you take the sun, for example, that has a very long lifetime of 10 billion years, and you go to a star that has 100 times the mass of the sun, you can see that the more massive star will have lifetime that are much shorter than the sun. So for example, stars that are here, the very massive star, live for a couple of million years. And obviously the very small star here have a huge lifetime, sometimes longer than the age of the universe. So we would be able to find very low massive stars that were formed at the time of soon after the Big Bang that are still alive today. So let's try to see a bit what happens to different stars in this diagram. We'll start with our sun that is here. So the sun during its life will slowly climb here at roughly constant surface temperature, but the luminosity of the sun will increase quite a lot during its life from the start to the end. There is an increase of a factor of at least 2 or 3 during this time. So this is maybe a bit of concern about the life condition on the Earth, because during the following billion years, the luminosity of the sun will increase, and thus the energy flux that the Earth will receive will increase as well. So the temperature of the Earth will increase in the more or less far future. After this, once the hydrogen reaction stops in the center of the sun, it will go to redder temperature, so cooler temperature. It will become red and becomes what we call a red giant. It will expand a lot. It's not exactly clear what will be the biggest radius of the sun, but it can easily go to our, 100 solar currents, solar radius, for example. So it is possible that the inner planets of the solar system at that time will be engulfed by the sun. So maybe Mercury or Venus, or maybe the Earth can be engulfed at this late time of the life of the sun. And once the sun is a red giant, the luminosity will then continue to increase during the late stage, and then he will go to the white dwarf region here at the very end of its life. If you go to more massive star, you can see that contrarily to this low mass one, the first part of their evolution is not at constant temperature, but they tend to cool a bit during the first part of their life. But again, the luminosity increase as a function of time, and then they cross this region here at roughly constant luminosity before it becomes red. For some stars, after the crossing, they have some kinds of loop that make them going back to the hot side of this diagram and then come back to the red at the very end. Massive star is a bit more messy. They can go to the red and then come back to the blue. They tend to end their life here in the blue instead of ending here in the red. So this is very dependent on what you put in your stellar models. But as we saw previously, the massive stars are very interesting for producing the heavy elements in the universe. So it's important to study them as well, even if it's a bit less secure than the low mass ones. Another important diagram is what happens inside your star. So here you have a plot where you have the temperature here in a logarithmic scale and the density here. And you have different regions in this diagram depending on what are the physical processes that take place in different places. So here in the center you have the region that is dominated by the perfect gas. So most of the stars, for most of their life, will go through this region here. So this can be a bit surprising to see that indeed a good equation of state for a star is a perfect gas one, because the density and the temperature are very high, and you can expect that this approximation is not that good for this kind of conditions. However, the temperatures are so high in stellar interiors that the material can be considered as fully ionized. So the typical particle you have in your gas is not atoms that are quite big, but indeed you have only protons and electrons that are completely separated life. So the particles you have to consider are much smaller than the atoms, making the perfect gas assumption valid again in this region. The size of your particles are small compared to the volume you have due to this ionization. Then you have here at low density but high temperature a region that is dominated by radiation. So if you go in this region here, your pressure will mostly due to the photons and no more to the gas pressure. On the other hand, if you go here at high density but less higher temperature or to very high density, you have different kind of degenerate gas. So you have here the gas that is non-relativistic but still degenerate. Then you have here a region where the gas is relativistic and degenerate, and so on. At still higher temperature, you will find again this kind of reaction that we already saw during the primordial nucleosynthesis. So you have pair interactions, so two photons are able to make pairs of electrons and positrons, and at still higher temperature you even have protons and electrons that are in equilibrium with neutrons and neutrino. So what happens in our models is here. So you have, we'll start here with this. It's the same diagram as before, so it's the central density of the star versus the central temperature of the star at different phases that are highlighted in color. And the typical time spent during the phase is indicated here. So this is for a 25 solar mass star. So the star starts its life here at a central temperature of 7.5. So I don't know, it's something about 25 or 30 million degrees. And during hydrogen burning, the temperature will progressively increase, the density will increase a lot, but it will not change dramatically during this phase. That is quite long. It's 6.25 million years for these models. Then the hydrogen burning will stop, and this will produce a collapse of the star because you have nothing more to sustain your star against the gravity. During this phase, nuclear burning will produce the heat necessary to counteract the gravity through the pressure. But when the nuclear burning stops, you have nothing more to sustain your stars against gravity. So your star will collapse very quickly in a few hundred of thousand years, even less. This is helium burning. So in a few, probably 1,000 years, your stars will go to very high temperature and very high density, up to a point where it is able to ignite helium burning. So again, helium burning is a steady state where the star moves slowly towards higher density and temperature. And again, at the end of the nuclear burning, you have a collapse up to the point where the next burning is possible in terms of density and temperature. And then the tracks begins to do some kind of strange path through the different burning phase. And you can see that the typical time of the burning phase becomes shorter and shorter. So hydrogen burning is a few million years, helium burning is a few thousand of years, carbon burning is a few hundred of years, neon burning is a few days, hydrogen burning, oxygen burning a few days as well. 50 days, 150 days. Silicon burning at the very end is very fast. It takes only 3 days to burn all the silicon inside a massive star, for example. We'll come back later to this different kind of burning and typical time. If you look at different kind of model, starting from the lowest mass here to the higher mass here, you can see that typically the tracks are roughly parallel here in the perfect gas region, but the slope is not the same as the slope that determines the region where the degeneracy becomes important. So at the end of their life, at least the lowest mass stars here tends to go in this region where you cannot neglect the degeneracy of your matter. On the other hand, you have here an unstable region that is very difficult to reach for stars that tends to go below this point. The gray zone here are the different burning phase. So here it's hydrogen burning, helium burning here, carbon burning here. So you see that the lowest mass stars are not able to go up to carbon burning, for example. They stop before because they are not massive enough to reach high enough temperature to burn carbon, for example. So this is basically how the central conditions evolves in stars. So we have two kind of very used diagrams in stellar physics. The one that relates the surface conditions, so luminosity and temperature, the Hertzsprung-Russell diagram here, that allow us to know what happens to the surface of the stars and what will be its appearance in the sky, for example. And this diagram here that linked the central condition of the star that will determine what kind of burning the star is able to reach and what kind of nucleosynthesis will take place inside this kind of stars. So to summarize a bit things here, as I mentioned, you have for different kind of stars, you have different kind of fate. And there are different names for this mass domain. So let's start here. We have something that we call the low mass star that starts from roughly 0.1 solar mass to 2.2 solar mass roughly. So this is the minimal mass to be a star. If you have less mass than this one, you will not be able to ignite the hydrogen burning, and you will be a brown dwarf if you are close to this value, or a planet if you are at still lower value of the mass. So these low mass stars will be able to go through hydrogen burning for the very lowest mass one, and these stars up to roughly 0.5 solar mass will even not be able to ignite things after the hydrogen burning. So they will basically stop their life after hydrogen burning and produce helium white dwarf. The point of these stars here is that they have a lifetime that is so long, probably more than 100 billion years and so on, so that none of these stars have had time so far to reach the end of their life since the beginning of the universe. So all of these stars are still burning quietly their hydrogen, and it will continue for a huge time. Then when you go to stars that have a higher mass than half the mass of the sun, they will be able to ignite helium after the hydrogen burning. So depending on the way the helium is ignited, if it is through what we call the helium flash, or if it's done steadily at the center, we have different kind of denomination. So the low mass star stops where a flash is needed, and if the flash is not needed to ignite the helium, we enter the intermediate mass star regime. But basically, the end of the evolution of this kind of star here will produce carbon-oxygen white dwarf at the end. So the limit for the helium flash is roughly at 2.2 solar mass star. So the sun is in this low mass star regime. It will ignite hydrogen and then helium, and then ends its life as a carbon-oxygen white dwarf. So from 2.2 to 8 to 10, we are in this intermediate mass star regime. If you still go to higher mass, from 8 to 10, maybe to 10 to 11, these masses are not very well known. So it's a bit, sometimes they can even overlap. It's not clear what kind of star will go through this phase. You can have a carbon flash, carbon ignition. So these stars will be able to burn helium into carbon and then to burn carbon. It will produce different kind of white dwarf, neon-oxygen white dwarf. And then when you go to mass that is bigger than 10, 11 times the mass of the sun, you enter the massive star regime. So these are stars that are typically able to go through all the nucleosynthetic process, producing silicon at the very end, exploding as a supernova, and the remnant for this massive star domain is a neutron star or even a black hole. So these are a bit the different terminology you will hear if you hear people talking about stellar evolution. So basically, low mass stars, intermediate mass stars, and massive stars. So from 0.08 to roughly 2.2, and then between 2.2 and let's say 10 intermediate mass stars, and above 10 the massive star domain. So I think I will stop here for the first part.